Hi, I'm Fernando Pereira from UFMG Brazil, and today we continue talking about control flow analysis, a technique that compilers use to understand the flow of information across functions in a program. To solve this kind of analysis, we will introduce a system of constraints, as we will be explaining soon. The algorithm that we use, as I've said in the first class, is based on the work of Alan Shivers from PLDI 1988. But we'll be using the notation from Nielsen et al. In the book Principles of Programming Analysis. The key references appear at the end of the fourth class on the subject. To explain how control flow analysis works, we will do it in three steps. First, we will specify the problem formally, explaining what a correct solution to this problem must be. Then, as a second step, we will show how to extract constraints from the program's code. A solution to these constraints satisfies the requirements stated in the first step. Then we will introduce an efficient graph-based algorithm to solve these constraints. We will do all the explanations over this toy functional programming language, which is a subset of ML. But the important thing is that the baseline language does not matter much. Any language that supports dynamic dispatch of function calls could be analyzed in the same way. So here's an example of program written in our toy language. Notice that our grammar has syntax to specify constants, variables, lambda expressions with the FN declaration, function applications, conditional expressions with the if-then-else, syntax, let bindings, and binary operations. We will not specify the kind of binary operation that we support, for that's not really important to our presentation. But notice that our language is pretty much a subset of standard ML New Jersey, for instance. The solution to control flow analysis associates information with variables and with labels. Variables are straightforward. These are the names defined in the program, like x and y in this example, on the bottom. The labels are a bit more complicated. They are used to refer to each part of a program that we can describe via a production rule in our grammar, and that can represent a function during the execution of that program. So we can imagine the labels like nodes in our abstract syntax tree. The goal of the control flow analysis is to map variables and labels to the functions that can be bound to them. This mapping will be called a cache whenever it refers to labels, and an environment whenever it refers to variables. Notice that we could use the same name for both. It's just that labels and variables are entities with different types, but we will map them to the same thing, sets of functions. So here we have three attempts to solve control flow analysis for the example on the top of the figure. The third solution, the one on the right side, is okay, but it's a bit too conservative. Basically, it says that any variable or label can be mapped to any function. It does not add much knowledge to what we knew before. The second solution, the one in the middle, is actually wrong. Notice that in the example program, variable x will be eventually replaced by the lambda expression that uses y as an argument. But that solution does not account for that. In the first solution, the one here on the left, the solution is actually correct. It gives us very good information. So it's less conservative than the third solution, and it's correct, as any function binding that could occur in the program is accounted for in the solution. So even though the third solution is too conservative, it's still correct. We want to know which functions might be bound to which variables. When I say might, that's just a hypothesis. If we say that every function can be bound to every name, that's not really wrong. It just does not give any information that we could use, for instance, if we would like to do inlining in the program. We will be representing our solution using this notation with a turnstile. When we say CR turnstile E, then we mean that the cache C plus the environment R satisfy the expression E. We have different types of expressions. Each type is determined by our grammar, which you can see here. So we need to specify which kind of pair cache environment satisfies each one of the possible synthetic categories of expressions. Let's start with constants. That's the C in our grammar. Any pair cache environment here satisfies a constant because constants are not really bound to anything. What about variables? Well, a variable is formed by two things: the name of the variable itself plus its label, L. Then we say that the pair CR satisfies the variable if the functions bound to the variable are a subset of the functions that might be bound to the label that marks it. So here we have the constraint that determines when this solution is valid. What about lambda expressions? A lambda expression is itself a function. So what we want to say is that this function is the only thing that can be bound to the label that marks it. In other words, we say that CR satisfies fn of x is E0 at label L if fn of x is E0 is in the cache of label L. Let's now focus on function applications. That will be trickier. So here we go. If we have something like T1, L1 applied onto T2 at label L2, like in here, then we must analyze each label recursively, like we are doing here. In other words, CR must satisfy T1 at L1 and it must also satisfy T2 at L2. That's the recursive part. Now, the complicated part. For each function that might be in the cache of L1, let's call it fn of x is T0 at label L0, like in here. So for any function like that, our par CR must satisfy T0, which is the body of that function. And anything that is inside L2, that is any function there, might be substituted by x when we perform the function call. So the function in L2 must be a subset of the functions in x. And the result of the application, which is the body of fn of x is T0 at L0, must be in L, which is the label of the whole thing. So we write that cache of L0 must be a subset of cache of L. Yes, that's a bit complicated, but if you think about it, eventually it will make sense. So at this point, I advise you to stop the video and then read what we have in the slide. The case for let is similar. When we have an expression like let x is T1 at L1 in T2 at L2, then we must recursively satisfy T1 at L1 and T2 at L2. That's a bit like the case of applications. And anything bound to L1 will be also bound to x due to the substitution that the let semantics implies. And finally, the result of the whole expression, which is the body T2 at L2, will be bound to L, which is the label that marks the entire let expression. Let's now analyze binary operations. That's an easy case compared to the applications and let expressions that we have seen before. When we have a binary expression, we simply analyze the two parts of it recursively. So if CR satisfies T1 at L1 and T2 at L2, then it satisfies the combination of T1 and T2 via a binary operation. I know notation was a bit heavy, but that's a good thing. Once we dive into the implementation of control flow analysis, if you go back into those figures, you will see that basically they are describing declarative programs. We could even implement those programs very easily in a declarative language like Prolog or ML. That would be a verifier that checks if a par CR satisfies a given program. In this class, we use a version of control flow analysis that's called 0-CFA. CFA, of course, stands for control flow analysis. The 0 means that the calling context is not really important. In other words, when we analyze a function f, we do not really consider the function that called f. If we did, then we could have a more precise analysis, but then it would be much more complex to implement it because calling contexts increase tremendously the amount of possible entities that need to be analyzed. Imagine, for each calling site, we would have a whole path of functions calling functions. By disconsidering context, we lose some information. I will illustrate this with an example. Consider this program, for instance, which terms can be bound to a variable x. Here, there is only one x in this program. You might stop the video and think about it. Well, the algorithm that we shall describe in this presentation will give this result to this program. We haven't seen this algorithm yet, just now trust that this is the solution that it will find. Notice that we consider that r of x can contain the two functions in this expression, namely fn of x is x at label 1 and fn of y is y at label 6. And as a consequence, the whole expression, which is represented by label 9, can also be bound to the two functions. But in practice, this will never happen. If we run this program, only fn of y is y can be the result of the program. Take a look into the program and try to convince yourself that only fn of y is y can be its result. You can stop the video to think about it. The analysis that gives that conservative solution is imprecise because it cannot distinguish the invocation of f at label 3 from the invocation at label 4. It's just function f regardless of where it's called. That's what I mean by not being context sensitive. To simulate context sensitiveness, we could rename each f at the invocation site, like in the program below. In this case, we would have that f2 can be at x1 and that fn of y is y can be at x2, which would be the result of the entire program. Anyways, the algorithm that we shall introduce now will not really do this kind of renaming, so we will have to live with imprecision. So that's it for the satisfiability of solutions. In the next class, we shall explain how we can generate constraints for a program. Thank you.